Yeah, so thanks again for having me. I'll be speaking about BlinderSwap, or where MEV meets MPC. I'll start by a very brief motivation on miner extractable value and with example of front running. And then I'll separate the talk to two parts. One is our high-level design of BlinderSwap, how we can build a layer 2 MPC-based solution to cope with MEV. And then the second part will be about an extension to Blinder, which is a system for anonymous communication, anonymous broadcast, to be more accurate. So I just want to start off by relating to Phil's talk from yesterday when he gave a definition of MEV. I will not repeat it here, but the key points in his talk were that in some sense MEV is unavoidable, and most or even all of solutions out there, they don't. There is no such an ultimate solution, but rather they move the problem from being in the wild where everyone can exploit the system into a more manageable zone. And in this sense, our solution based on MPC is of no difference. We as well move the problem from being in the wild into a more permissioned zone where if our assumptions do not hold, then the MEV problem is also not solved. And I think this is actually relevant to all MPC-based solutions. So one thing that I want to propose is a characterization of the conditions when unfairness occurs. And I think that unfairness occurs when we have the combination of three conditions. The first one is when we have unregulated super players. And later I'll show you how those three conditions actually hold for a system like Uniswap or Ethereum in general. The second is where intents and execution, there is a time gap between them. So what I call intent is just a signed transaction that is ready to be executed, but it's still not executed. It's not mined yet. It's just in a mempool, for example. And last one is leakage of intents, where intents are being leaked to those super players. When those three conditions hold, then there is the opportunity to exploit the system for front running or general MEV. And the Uniswap, for example, has those three conditions hold in Uniswap, which is one of the most popular exchanges. Decentralized exchanges, which also have volume that exceeds even centralized exchanges. So solutions to situations like this, where the three conditions hold, could be government regulation. For example, market makers could not take some actions based on the information they have, or like inside information that several key points in a company have, they cannot act upon them. So in centralized market, we have a lot of regulations on such stuff. And MEV is not like, of course, the problem is not relevant only to the decentralized world. It exists also in centralized world, but there we have the regulation. But in the decentralized, we need to find other ways to combat those issues. Other solutions include reputation system like Flashbots, and other MPC-based like the Anoma blockchain, which is actually a layer 1 solution, or Honey Badger Swap, and what I will speak about today, which is BlinderSwap. A very simple example of how those three conditions, when they met, it could someone could exploit that situation is very like maybe one of the most famous attacks on Uniswap is called the sandwich attack. In this attack, we have an honest user who tries to trade. For example, he wants to buy DAI tokens using its ETH coins. Then it simply sign a transaction and sends it to the Ethereum nodes, and then it just the transaction just lies in the mempool. And when a miner takes this transaction and wants to actually mine it, put it into a block, then it can wrap it by 2 other transactions. The first one will do exactly the same as the honest user, trying to buy DAI tokens using ETH coins. And the other one, this is the first one, and the other one will do exactly the opposite. It will take the DAI tokens that were given in return to the ETH token, to the ETH coins here, and give it back to the market and receive in return other ETH coins. Now, when there is an honest transaction in between, this leads to the situation in which the amount of Ethereum coins that the miner begins with is smaller than the amount of ETH coins that the miner ends up with. And this is actually very simple attack that in which a miner can take a position in the market, but without any risk. He just knows it's going to win some ETH coins. And the fact that there is no risk to the miner is very problematic. This is at the core of the fairness problem. Because usually traders, they take a position, but they know that there is some risk, right? So when we think of an ideal solution to that problem, the first thing that we have to deal with is how to fairly order the transactions, right? Well, in the example that I showed before, the transactions were ordered by the super player, the miner. But in a solution, we want to make sure the ordering will not be actually affected by the super users. So first, we have to decide which type of ordering we want. In a solution that does not split the time to intervals, we can do first in, first out. And yesterday there was a talk about fair ordering Byzantine agreement that tackled that kind of problem. They attach a timestamp to each message, and then the messages are being added to the ledger using that like according to the timestamps. Other solutions, other ordering could be random, where we do split the time into intervals. We can take the batches, like a lot of transactions that got into the system within period of time, and we can randomly order them so that the traders could not have special power on where their transaction will end up. At this, if we actually take the random ordering, then such an attack that I showed before, the sandwich attack, will not, with high probability, will not succeed, because it might be that both the transactions of the miner will be after or before the honest user transaction. Another approach that I've not seen so much in solutions yet, or I'm not sure that I know all of them, but is a spread approach, which takes all the transactions within a period of time. Then it can aggregate all of them. For example, all those transactions that want to buy DAI tokens for ETH coins, they can such a solution can aggregate all those transactions into a single trade, and then the DAI tokens that it gets in return can be spreaded evenly to those traders. So that's another approach that could be taken, but I've not seen it so far. And we have to make sure that, like at the core of the ordering problem, we want to make sure that the position that is taken by the miners or the super players is independent of the position taken by honest users. This is what is called in MPC literature as the independence of inputs property. Except that there are the natural properties that we would like a system to have, like robustness. So we don't want anyone to be able to deny service, and censorship resistance, which means that we want users to be able to post their transaction or trade request without being blocked, even if one of the operators of the system is malicious. So a functionality that we will implement is actually taken from the Blinder, the Blinder protocol. This is the protocol that Blinder implements. This is the functionality that Blinder implements, which is called anonymous committed broadcast. The functionality, you can think of it as trusted party that do whatever we tell them in this box, but later on it will be implemented using secure computation protocol, using several servers. So what do we want the trusted party to do is to initialize a table A with about n entries, where capital N is the number of clients or number of messages or trades. And for each client who wants to input some message into the system, it just sends its message, MK, and the trusted party picks a random entry in the table and puts MK in that entry. Now, such a functionality gives us the following guarantees. Let me start with censorship resistance, or which is actually achieved using the anonymity property of that functionality. It means that when nobody, let's say we have that trusted party, and we see the output of that trusted party, which is the table A, and we know all the clients that were communicated with the trusted party. We cannot associate a client with with its message, because we don't know where is that message of the client. This is the purpose of this randomization of order. So by this anonymity property, we actually achieve censorship resistance. Yeah, and robustness means that like in a box that actually specify functionality, if there is no robustness, that we usually specify that at some certain point, the adversary may send a message to abort the execution. But here, since we don't have this, it means that there is no such ability to the adversary, and the functionality is robust. And we achieve here a fair batch ordering, because no client has a power of where, in fact, here in this specific functionality, no, I'm sorry, because no client has power to specify where exactly its message will be end up with. So we want to use such a functionality to try to mitigate the MEV problem. So what I'll do next is describe our simple design, which we call BlinderSwap. It consists of 3 layers. The first layer is an on-chain permission contract, a BlinderSwap contract. The second layer is the implementation of this anonymous committed broadcast functionality, or ACB. This is the layer 2 part of the system. And then we have all the clients. And if you care about numbers, then the ACB could be implemented with tens of servers, and it could serve from 10,000 to 100,000 clients, or even more. And actually, in our Blinder prototype, we had we could be able to serve a few millions of clients. Okay, so the system will operate in batches, where in each batch, all clients will send their transactions in a secret shared manner to the anonymous committed broadcast functionality. Then the functionality will split all of them in a random order. The random order is specified by the functionality, and then the contract will execute the trades in that specified order. And there are several subtleties that have to be taken care of. The first is that transactions will not necessarily arrive the contract in the order that is specified by the functionality. And to make sure that they will be indeed executed by the order specified by the functionality, will separate the messages from the functionality to the contract to two. The first one will contain a lot of transactions. They do not have to be bundled. They could be sent to the contract in any order. And the second message will have the permutation specified by the functionality, in which the contract will execute those transactions. Now, another issue that has to be little issue that has to be solved here is how the clients will pay for the service and how they will pay for the miner, right? So what we specify for the contract is that the contract, whenever it receives a transaction, it only stores it, or it maybe parses it and store the trade request in a simple way. And it waits for the second message of the ordering from the functionality in order to start the execution. So the transaction will pay two types of fees. The first type of fee will be paid to the miner, only to execute that simple parsing and storing within the contract. And the second type of fee will be paid directly to the service that implement that ACB functionality. And this payment will be part of the logic of the contract. We want the service to be paid such that the operators will not lose money, of course. Now, how the traders know what will be the actual appropriate gas price to put in their transaction to pay for both the miner and the service? As I said, we want the service to be profitable because this is what makes it actually work. And what we propose is that the servers that operate the ACB functionality, they will post before every epoch, they will post the expected gas price, right? And when they open all transactions at the end of an epoch, the servers check for each transaction whether the gas price specified in that transaction meets that expectation. And if not, it will just be discarded. And this type of proposal has a potential of being used as a gas price oracle. Currently, I don't know good applications for gas price oracle, but if you know some good applications, I'll be happy to hear. I want to relate also to the honey badger swap approach that Yunchi has described yesterday. In terms of the function, BlinderSwap operates more as a relay rather than a custody that honey badger swap takes, because HBSwap takes the funds of the trader into some secret wallet that is operated by the MPC servers, and we can look at it as a custody. And in that sense, I think that it adds a little bit of risk to the traders. On the other hand, in terms of privacy, BlinderSwap has privacy only during the epoch, whereas honey badger swap or Anoma has always privacy for even for different types of different values in the exchange. For example, the pool size and how much of the trade request was matched, and what is the balance of each user, and so on. In terms of ordering, BlinderSwap can do either random or spread, whereas honey badger swap and Anoma can do any type of ordering, including actually the first in, first out, which we can't do. And I'll use the remaining minutes to describe Blinder++. It's actually an extension to Blinder. So Blinder is implementation of this anonymous committed broadcast functionality with small n servers and capital N clients. And the adversary may corrupt up to n/4 of the servers and any number of clients. And of course, the number of honest clients, they actually consist of the anonymity set. So the larger the number of honest clients, the larger the anonymity that they get. Now, one second. What's going on? Okay, sorry, it just jumped. So as I said, the time is separated into intervals, and in each interval, the servers receive a lot of, accept a lot of clients. So each client picks a random location I out of from 1 to capital N, and it generates a vector of n Shamir sharings, where all of those sharings hide the value 0, except one that hides the value of the message. And this is actually a random location picked by the client. And then, for example, you can see here the vector of each client. We have 4 clients here. At the end of this, the servers take all of those vectors and they sum them up into a result vector that contains all of those messages. And this is a very simplified example in which the clients do not collide. Their messages do not collide. And this addition could be done very easily locally by the servers, because it requires only addition of Shamir sharing, which does not require any communication. However, the vectors, if the number of clients is large, the vectors will be very large, and it will not be very efficient, communication efficient. So for efficiency, we can a client can compress its message into 2 small vectors of size square root of n, where in the row vector it puts its message in one location, random location. In the column vector it puts 1, and it sends those sharings to the servers, and the servers can do the multiplication of those 2 vectors to obtain that matrix. And now this matrix is of size n, the number of clients. Now, from this point, the servers can continue doing the addition of all matrices from all clients, and obtain a final matrix with all messages of all clients. Okay, so this is what I call decompression. Of course, at the end, after the sum up, the servers open all entries in the final matrix, and yeah, and from that point, we cannot, as I said before, we cannot associate the client with its message, because only the client knows where its message is. It picked the location randomly. About efficiency, so asymptotically, we have for the client, we have communication that is linear with the number of servers and square root of the number of clients, and the server communication is only linear with the number of clients, but the computation is quadratic in the number of clients. But this compression of all clients can be done. We could reduce this operation to a simple single matrix multiplication, which could be run over GPU, which actually gave us very good performance. For example, with 5 servers and messages of 1 kilobytes, we could serve about 10,000 clients in about 8 seconds, and about 100,000 clients in about 1.5 minutes.
5-minute warning, by the way.
Okay, thank you. Now, about real-world deployment of Blinder is something that I hinted before in the MPC panel. Let me start with to repeat that the fact that clients input their entries of the vectors using Shamir sharing, right? That means that each client send a different share to each of the servers. So in a synchronous network, when some server misses a share, or when it is given an incorrect share from a client, then these 2 situations are treated the same way. And we can handle this situation in Blinder thanks to the fact that we assume synchronous network, because those two situations are treated the same way. We could do some kind of protocol that involves player elimination to decide whether, whenever we see an incorrect share or a missing share, that is this is the fault of the client or the fault of the server. And if we find out it is the fault of the server, we just eliminate that server from further computation. However, in an asynchronous network, these two situations are not treated the same. Could not be treated the same. And servers must decide which client to serve in the current epoch. So if some server claims that it didn't hear from some client, the servers have to decide what to do. One solution would have the other servers that did get their shares from the client. They could securely compute the share of that servers that didn't get, but this would be very expensive if we have to do this a lot of times. The second solution, possible solution, would be that we just discard that client from this batch and maybe delay serving it in the other batch. But this will lead to an insecure solution, because now a malicious server could just claim that a lot of honest clients did not send him their shares. And if we just discard those clients from the system, the result will be that the anonymity set will be dramatically reduced. So we don't want to go this way. Another way to input a value into the system could be something that we call robust input method, that is actually used by other protocols, including Honey Badger MPC, in which the servers just generate a random sharing R, and then to input a secret X, and the client computes the value delta, which is R minus X, and broadcast delta to the servers. And now the servers can locally compute the sharing of R minus delta. They can do this locally without communication and obtain a sharing of the input X. Now, the problem with this, sorry, let me start with the good thing, is that we avoid the server's claim of missing or incorrect shares. Now, because we use broadcast, then all honest parties agrees that we did get input from that client. But the bad thing is that the number of shares that the servers will have to generate is really huge, because each client, the input of each client is order of square root of n. So this solution is good in terms of security, but it's not efficient. What we do, sorry, how much time remains? 1 minute.
Just about a minute, yeah.
Okay, so let me do this. What we do is what's called hierarchical pseudorandom secret sharing. So a property of pseudorandom secret sharing is that it allows to generate a lot of pseudorandom sharings out of a constant number of them. So for example, 1 out of 3 replicated secret sharing, we have party 1 having x1 and x2, party 2 have x2 and x3, and party 3 has x3 and x1, where x1, x2, and x3 are all random. So the sum of all of them is S, which is random as well. And now one party could not learn the secret, but any pair of parties could actually combine their values and learn the secret. What's nice in this PRSS is that we can expand those values that the parties have, looking at them as seed to PRG, and then generate a lot of pseudo-random secret sharing. Now, if party 1 expands its second row of x2 using seed x2, and party 2 also expands x2, then they get the same row, of course, right? So we can use each column in this matrix is actually a new random pseudo-random secret sharing. We can associate each such column with each client, and then expand again. This is what makes it hierarchical. We can expand.
We are running out of time rapidly.
I just finished.
Okay.
Okay. So we expand it again to get a lot more random secret sharings, and each column is given, and this full matrix is given to that second claim. Yeah, I'll not talk about this. I'll just finish here. Thank you.
Perfect. Thank you very much, Avishay.